Hello. Okay, we're here. Are my other MSI tutors here? I only see one. No, Joyce? What? Do you know what the other guy's name is? Syria? Are you here? Okay, so we have a third MSI tutor, even if the, oh, this is bad. Just a second. I can't deal with this. Okay, I think that's better. We have a third MSI tutor. What, say it again? We're still just looking at the bunny, if that's not what you he's pretty cool, though. So go sign up for MSI. We will only have alternative methods to get 5% extra credit if MSI fills up. And MSI very positively correlated with high grades. I will have office hours on Monday from 11 to 12, and all Mondays going forward in the future. If you want to talk to me other times, I'm willing. Your TAs are all having their normal sections. We are not having a quiz today. Someone out there walked up and said, we don't have a quiz today, and I said no, and he left. We are having a quiz on Monday. That makes this the virtual Wednesday, which is to say you guys are here. Do you know what? We now have a collaboration to decide exactly what's on the quiz on Monday. Okay, this is what I think I'm going to put on it. Something from the homework that was due Wednesday, plus, shouldn't I have what? Right now, they're not putting up the recordings. We still don't have Wednesday's recording up. They say they're having technical problems. So aren't you glad you're here? Something from the homeworks, and I'm going to give you a truth table, and you give me CNF. So let's make sure you can do CNF, okay? Yes? I'm having a little trouble hearing you. I don't think I put homework due dates on. I put quiz dates on. There's a quiz on Monday that corresponds to the homework that was due 2 days ago. And there's a quiz on Friday that corresponds to the homework that is due in 5 days. Are we making sense? It's just that today's quiz has been shoved to Monday because of Inauguration Day. I'm sure that all the empty seats have to do with people who are out protesting our new president. Or maybe celebrating. I do know people I love who voted for Trump. I just try hard not to think about it. Okay, we have 2 MSI tutors, and I want my new MSI tutor to tell me who he is so that I can figure out, you know, put him on the slide, get him a nice picture, that kind of thing. DRC, the DRC messages have slowed down. If you do have DRC accommodations, I would really appreciate having them early. I know there's at least 2 people who are still going through the process. You've let me know you're on the way. You've done your job. I'd still, as soon as you get your PDF, please send it to me. This is for reference. This is normal forms. Let's make sure you can pull CNF off of a table. Let's put down something that is got just as many zeros as it does ones, okay? So, okay, for each line, shout out 0 or 1. I'm going to put out the one I hear the loudest. Okay, first line.
0. 1. 0. 1.
Okay, that's our formula. 1 of 2 to the 2 to the third formulas that you can have for a 3-variable truth table. If you are writing down CNF, there are 2 approaches you can use. I'm going to divide this white space at the bottom into 2, write 1 answer using 1 technique in red, and then I'll use the same answer using a different technique in blue, okay? So you can see both. So, this is the way, let me tell you how I do it. I look at the 0 lines of the truth table. I say, my job is to tell whoever is watching this to communicate how to stay off of the 0 lines of the truth table. So I write down a row for each 0 line of the truth table saying how to make sure that your variable assignment does not leave you on this row. And then I and all the rules together, because it doesn't do you any good to stay off the top line if it just pushes you onto the bottom line, right? I always think of it in terms of chessboards. If you win when you're on a black square and I tell you how to avoid the white square in the corner, that's no good if you just hop over 2 and you're on a new white square. You still lose because you're not on the black square. Am I communicating by analogy? Okay, so top line. How can we make sure we are not, I was going to do this one in red. How can we make sure we are not on that line of the truth table? We just make sure at least one variable doesn't describe the first line. Well, if P is true, or Q is true, or R is true, you can't possibly be on the top row of the truth table. Any one of those is enough, right? I mean, if all of them are true, then you're really not on that line, but it's sort of like being pregnant, right? You're either on the line or you're not on the line, right? Enough, no more discussing pregnancies. Think of some other binary conditions I can use then. It's just pregnancy is so...
How about transistors?
You and I will be happy with transistors. Other people will not. Okay. So that's the rule for the top line of the truth table, but we have to make sure that we include the rule for every 0 line. So for this line, you are not on that row of the truth table if P is true, or Q is false, or R is false. For this line, you are not on that row of the truth table if P is false, or Q is false, or R is true. And for this line, you're not on that row of the truth table if anything is negated. Okay, that's it. You're done. Completely done when you do that. But some people, and I'm telling you, as a dyslexic person who has trouble organizing things and loses small pieces of paper and just has problems in that general area, before I understood this on a really gut level, which is what I would like best, that you understand it on a really gut level, when I was just trying to follow rules, I would look at that thing and I would say, wait a minute, how do I pull off the name of the truth table when I'm trying to do C and F? And I would get it backwards sometimes. So if all you want to remember is how to pull off the names of the truth tables in D and F, you can pull off all the 0 lines, write them down as if they were 1's lines, and then set the whole thing to false, and then negate both sides. It's more work to do it that way. But some people find it very instructive, so I feel like showing it to you, even though it's more work. Do you want me to show you this method? Okay, so may I, well, I'm going to, at the very least, I'm going to move that black line over so I have more space. Okay, so I'm going to do this one in blue. Okay, the name of the top row of the truth table, as if it were a 1's point, is P and Q and R. And I'm going to OR it together with all the other, as if they were 1's points, 0 points. So now I'm going to say that I'm going to try to put as many on the same line as I can. Next I have, why did I write it that way? Sorry, these should all have little negations in front of them. See, I better write this whole thing again. Okay, we're going to write it down as if it were a 1's point, which means we have to write it down for real. So it's not P and not Q and not R. And then I'm going to OR that with the next line, which is not P and not Q and R. And I'm going to OR that with the next line, which is not, oops, that was the wrong one again. I'm sorry. I did the second line and not that. I need to go down to here. So that should be not P and Q and R. And I'm just going to go ahead and put the next one here, which is P and not Q and not R. And then the last one, oh, that's wrong too, sorry. Okay, I'm going to take just 1 second, a nice deep breath so that I don't screw up anymore, okay? I recommend you do this when you start screwing up on your final, too. Okay, I'm going to shut my eyes. No, seriously. Shut my eyes. Everything's okay. Back. I will cease to make mistakes. I need to get these two lines. Did I get them? I need P and Q and not R. And together I need no negation. I need P and Q and R. And then I'm going to set that whole thing to be equal to false. Because what it is those, if you land on any of those lines at the truth table, your formula will evaluate to false, right? But we don't normally describe formulas in terms of how to falsify them, right? So what we really want to know is, how do we make it true? Well, how do we make it true? We negate both sides. So I'm going to move my black line over even more. See? So I have more space. And I'm going to put big old parentheses around the whole thing and negate it. And then I'm negate F. So all I did was take two things known to be equal to each other and negate both sides. Right? Make sense? Can I have some head nodding from the back of the room? Okay, good. Because sometimes I don't want to just teach to the front third of the room, even though I can see these people much better. Okay, so what happens now, and I'm not sure I should take the time to do it, but what happens now is just 2 layers of De Morganing. That's all that happens. Okay, so let's call the guy that's in here, let's call that capital A. The guy that's in here, let's call that capital B, capital C, and capital D. So now what we have is the negation of A or B or C or D is equal to the negation of false. So that's equal to the negation of A and the negation of B and the negation of C and the negation of D is equal to true. So now all you have to do is De Morgan again by taking the negation of A, since A is something and something and something and something, you will change it so it'll be the negation of something or the negation of something or the negation of something. Do you see what I'm saying? It's longer. It takes longer to do it this way. But for some people, it fits their mental process better. So I just want you to be aware of it. And I don't think it makes sense for me to take it any further. But man, whip out your little phones, take a picture of this, and make sure you can do it at home, okay? Don't trust the recording today because we still haven't gotten Wednesday's recording. So I cannot guarantee you that you will have today's recording by Monday. Right? So, take a picture of this and go home and do the next level of De Morganing, because you see A is the quantity, not P and not Q and not R up there. See it? Does everybody see how to do this at home? It will be better for you to dick around with it than to watch me dick around with it. That's the way human beings are. It's always better to get right in there. Okay, the next question is going to be something about sets. So let's start talking about sets so we can figure out what it could be. Sets, Pokemon. I don't have to remember their names because you guys are. I am only going to guarantee that I know who Blitzel and Zebstrika are. The other ones are, what? No, but these could be letters in the alphabet or pictures of stars and circles or numbers or names of human beings, right? You guys all work with online data these days, right? We think of them as sets. Computer scientists think of them as sets, and we intersect the sets, and we do all sorts of sexy things with them. We take cross products of them. It's great. Okay. They probably want to do the same thing for me. But they are really projected in there. They're really, yeah, they're really in there. I mean, like,
Luke, I am your father.
Okay, so things in sets. We very commonly use curly braces to denote set items. If I put Blitzel in there 7 times in that set on the top, it wouldn't make a damn bit of difference. Are you my MSI tutor? No? He's sitting near. I see Joyce. Is my other MSI tutor here? No, not Kyle. We have a third one. Somewhere we have a third one. Maybe he's protesting. Okay, so repeats don't make any difference. If I put Blitzel in that set, if I list it 7 times, it's the exact same set. An item is in the set or it's not in the set. It's not in the set 3 times. That makes no sense. Blitzel is the horsey dude inside the set. Zebstrika is the horsey dude not in the set. Horses are of equine gene, I forget what is it order, family? Yeah. It doesn't affect it at all. In fact, that's exactly the point. You are asking the question that is exactly what I want to emphasize. Thank you. So, for example, I can't obviously draw Pokemon off the top of my head, but this set, A, B, C, is exactly equivalent to the set C, B, A, C. Same set. Order doesn't matter, repeating doesn't matter.
Is the logically equivalent sign appropriate there?
I can give them names. I can say this set's name is S sub 1, and this set's name is S sub 2, and now I can say S sub 1 is equal to S sub 2. And I will take one line out of my equal sign. How's that? There. Yeah, no, that's good. I tend to use all my intuition for logics for set and vice versa. And I sometimes am sloppy about that. I actually welcome being forced to be more careful. Yes? Because it's like we talked about the concept of an idempotent operation online. Do you remember when we did that? How if I owed Kyle $1 and I hit a button that said give Kyle $1, add $1 to Kyle's bank account. If I hit that button 5 times, I give him $5. But if I have a button that says query Kyle's bank account for its balance, and it says $6 because Kyle's rich, and then I hit the button, and then I say set Kyle's bank account balance to $7. It doesn't matter how many times I hit that button, I get the same result. Being in a set or not in a set is something that that's the only answer there isn't. There is. I keep saying pregnant, but it makes sense. I mean, I can ask how far along a woman is if she's pregnant, but she's either gestating or she's not, right? There's no, like I'm 59, I'm not. Like I'm really not. I'm never gonna. It's a binary thing. An item is in the set or not in the set, and that's all there is. What it is it's set up to say that no matter how hard you try, you can't change whether it's in or not by putting it a few more times. It's kind of like the more often you scream something at a political rally doesn't necessarily make it more true, right? It's just in it or it's not in it. That's all there is. And there are times, especially with online data, like suppose I'm trying to take the intersection of people in CE16 and people who are members of Crown College. Well, if I have the set of people at Crown College and the set of people in CE16, there are going to be records that appear in both of these. In fact, that's what I want to know if I want to take the intersection of them. But I could just, if I wanted to take the union, I could list everybody who's either at Crown College or in CE16, and I wouldn't care if some people were listed twice. That doesn't make them any more members of Crown College who are in CE16. Could you raise your hand if you're at Crown College? Anybody going to chocolate night? Chocolate night. Chocolate night is some sort of celebration at Crown I've been asked to go to. I'm going to chocolate night. Any of you who are at Crown who want to go to chocolate night, you can wave hi to me. I'm not doing anything special. I'm just going. I don't know when it is. Some Wednesday. Okay. Keep asking questions. Questions are good. Okay. here's something that's really important. When you say something about a set, if somebody asks you something about if something is true about a set, you probably can't answer unless you know what the universe of discourse is. The universe of discourse is sort of, like for example, I can ask you questions about numbers, and the answer is different whether I'm talking to you about positive integers or all integers, for example. So if I don't make it clear, if I put some stuff up about, n squared always greater than or equal to n, that's only true if we're talking about positive integers. It doesn't work if we're talking about all integers, right? Because -3 squared is in fact greater than -3. Wait, that works too. What am I doing wrong? Oh yeah, that. Good, thanks. That's good. Yeah, sorry. Whew. Just having a bad day, guys. Okay, so element of. We love the little element sign. I see people who are just being introduced to set theory having a lot of trouble differentiating between element of and subset of. So I want to be really clear of it. Each one of these little dudes in this setup here is an element of that set, all by itself. If I look at subsets of that set, a subset is itself a set. So for example, one subset of this set would be the set containing Blitzel. That's a set. Blitzel is an element of S, and the set containing Blitzel is a subset of S. If you program, think about type matches. A subset is always a set. You could almost think of it as an array, right? Sets are often implemented as a bit array in programming languages. If your answer could be a single thing rather than an array, it's not a subset. That's something that you're probably thinking of as element of. Okay, we use element and slash through element a lot. So Zebstrika is not in S, but Blitzel is in S. Two sets are equal if and only if it is impossible to find an element in one that is not in the other. The way you say that in Mathese, and it's really an important part of this class that you become more comfortable saying things in Mathese. So I say this very informally. I say, hey, you can't find an element in one of those sets that's not in the other. That's great informally. How do we write that formally? For every object that is an element of S, it therefore must be true that the element is also in T. That's what the first part says. And also, for every object that's an element of T, it therefore must be true that the object is an element of S. Now you go through all objects in the universe of discourse. That's what that implies. You look at the object. For example, here, if we look for Zebstrika, who's not up there, we're never going to get past the guards, right? Think of it as the if statement in your program. So when we check on Zebstrika, Zebstrika is not an element of S, so we don't need to check whether it's an element of T for the first part. And then Zebstrika is not an element of T, so we don't need to check if it's an element of S. So Zebstrika is not messing us up. And when we get to Blitzel, we say Blitzel. Blitzel is, in fact, an element of S, so now we have to check, is Blitzel an element of T? Also, because of that and sign, once we see that Blitzel is an element of T, we must check to see if Blitzel is an element of S. It doesn't matter that they're in different or presented in different orders in the two sets. Okay, there's a lot of special sets. This is important. If you read a proof online that it concerns the natural numbers, check to see if 0 is a member of the natural numbers. I'll get this guy and then that guy. A member of the natural numbers, because not everybody says 0 is a member of the natural numbers. Okay, I don't remember whether I said front or back first. Back, okay, go ahead.
What is the upside down mean?
That means for all. For all, it means for every. And that actually was in 1.3. I haven't lectured on it yet, though. It turns out that when you talk about for all, it makes sense to talk about elements of sets. And when you talk about elements of sets, it makes sense to talk about for all. And so I just kind of went for it, and I'm going to assume that we're going to use it informally until we can use it formally. And there was a question in this area. Yes?
So, like, what exactly is the universe of discourse? Is it just like
whoever's posing you the problem has a responsibility to make it clear to you what the universe of discourse is. For example, I might say, for all letters in the English alphabet, none of the letters have inherent accents over them. I can say that in mathese. Or for all letters in the English alphabet, none of them are pronounced using that exclamation tongue click sound from Africa. You know,
Has the universe of discourse been covered in lecture yet?
that's what we're doing. The universe of discourse is something that it doesn't make sense to talk about sets until you understand what a universe of discourse is. These set names are being given to you now because they're going to be used mostly as universes of discourse. For all x element of integers, x element of integers, x squared is greater than x. I think that's greater than or equal to x. Okay, element of integers. That's not true if your universe of discourse is real numbers, right? Because now if you square 1/2, you get 1/4. Okay, so I will be using these symbols, but I'll be making it clear what I mean a lot. I just want you to get used to it. Once again, I want to make sure the kinds of errors that I see a lot. The empty set is exactly the same as set braces with nothing in it. So that if you do a for all, it's kind of like you have a for loop, and your for loop says for I equals 10 to 1, step 1. So you're trying to step up from 10 to 1, and it will never happen because nothing will ever happen in the for loop, right? The empty set is set builders with nothing in there. If you have a set indicator and you put another set inside it, it's not the empty set. This is the same as a set containing the empty set. And it turns out that a set containing an empty set is something that happens a lot. You're going to see it in our proofs and things. The cardinality of a set containing the empty set is 1. There's one thing in there. It happens to be a set. Yes? That means I want you to think of it as being integers, but I only care about the positive ones. Because normally we think we want it doesn't make any sense to have both of them be negative because you're just being redundant, right? So -1 over 4 is -1/4, and that's the same as 1 over -4, but let's just put the negatives on the top. Okay, and you can't have any zeros on the bottom, so you already had to restrict the bottom anyway. Hey, and if you're trying to avoid zeros, you could just go ahead and avoid the negative numbers, and then you don't have to you don't have to come up with mathese for, and by the way, only one of these things should be negative. So it's just for economy of notation. It would be completely legitimate to do it a slightly different way, but this is the normal way. Mathematicians tend to be very pleased and charmed by brief ways to say the same things. So for example, if you ask an average mathematician, here are 2 proofs that prove the same things. This one is 3 lines long, and this one is 5 lines long. Almost all people will say the 3-line proof is better, assuming there's no errors. Like, it's considered very good to be able to state things with brevity, and sometimes that leads to a certain amount of confusion. Am I making sense? Okay. Let's keep going, and I know that I'm throwing a lot of terminology at you. On the quizzes, I don't go out of my way to force you to have memorized this. I will have a tendency to say is a member of the natural numbers scripty n. That's not what I'm trying to get at. We talked about denoting sets. One is I could just list, what all the sets are. I'm going to put a heart in this one because there's an extra comma there. I don't know why there's nothing there. We use brackets for ranges of real numbers, like all the real numbers between 0 and 1. For example, one of the things that you guys are going to have to study in this class and that you're going to hate me for, at least temporarily, although it's pretty damn cool and you ought to love me, is we prove that the set of real numbers between 0 and 1, non-inclusive, is not countably infinite, which is actually really cool. It is infinite, but it's not countably infinite. It's a greater order of infinity. That's when you learn about the absolutely marvelous, oh my God, I read science fiction concept of Aleph, that there are orders of infinity. There are orders of infinity that are more infinite than other orders of infinity, which just makes me feel like I'm reading George Orwell. But if you're talking about cardinality of a finite set, then the cardinality is just the number of unique elements. That's all it is. But it is exceedingly common in computer science and mathematics to deal with infinite sets. Cardinality of infinite sets is harder. And what we want when we talk about cardinality of infinite sets is we come up with a one-to-one correspondence of a set we've already agreed on the size of. For example, we can do that with non-infinite sets too. So the set of all x such that x is an element of an English alphabet, that's 26, known to be 26. I can make a one-to-one correspondence with the integers between 1 and 26 and the letters between a and z. Therefore, they must have the same cardinality, right? I mean, it sounds like, you know, I took out my sledgehammer and beat that ant to death with it. It seems like overkill, but that's the technique we're going to use when we talk about the cardinality of infinite sets. Okay? This is really important, guys. You need to understand these two lines, like on a gut level. You need to understand that the cardinality of the empty set is there's nothing in there. It's 0. But the cardinality of a set containing the empty set, there's a thing in there. It's a thing. It's an important thing. Okay, so countable versus uncountable. If you can index a set by the natural numbers or any subset of the natural numbers, the set is countable. That's really important. We're going to be using this a lot. So for example, I have here, I'm showing you that the odd positive integers are, well, I'm not going to say it the bad way. I'm going to say it the right way, and then I'm going to say it the bad way, and we can talk about why there's a bad way. The right way to say this is that the cardinality of the positive integers is the same as the cardinality of the odd positive integers. Now, does this freak you out? Be honest, man. If this is the first time you've seen this and this does not freak you out, you are way too placid. Like, this should freak you out. I mean, everybody in the bottom row is in the top row. There's guys in the top row that aren't in the bottom row. So this guy on the bottom is a subset of the guy on the top, and I'm telling you they're the same size. I mean, shouldn't that freak you out?
It's weird, but it's true.
It's weird, but it's true. But here's the thing. I've seen this happening. I want to make a big deal out of this because I want you to be able to enjoy it. It happens that there are a lot of really hard things to understand at the beginning of computer science. And if you just don't worry about them too much and you do them enough times, it'll become usual to you and you'll stop worrying about it. That's not the same thing as embracing the weirdness, seeing what's odd, getting to the point where you can see why this makes sense and is consistent with the rest of the approach of the discipline you're studying, and then not being upset by it. Now, I think you can fake the second with the first. And not only that, I think the first eventually turns into the second. But I'm saying that for me, there is something to be gained by noticing what's weird about something. For example, programming. When I first learned programming languages, there was something that really bothered me about x gets x plus 1, right? Assigning x plus 1 to x.
Oh, yeah.
And it was years before I figured out that things that appeared on the left-hand side of the assignment were automatically dereferenced, and I was placing them in a memory location, whereas the things on the right-hand side, I'm looking at the value. But it took me years of programming before I noticed that. And I think if somebody had gone out of their way to point that out to me when I was learning to program, my understanding of pointers and the difference between an address in memory and the contents of memory at that address would have progressed faster than it did otherwise. So what I'm recommending, and this may just be me, so you feel free to ignore me if you work differently. When something that is weird as shit happens, embrace it, suck the weirdness out of it, see why it makes sense for it not to be weird, and then move on. Don't say to yourself, oh, she says they're the same size. I think she's crazy, but she's in charge of what grade I get, so I better play along. Okay? I'm recommending that you embrace the fact that the bottom row of numbers is a subset of the top row of the numbers, and yet the reason it's a one-to-one correspondence is what number is with 13 on the top, what's going to be on the bottom? 25. Okay, with 500 on the top, what's going to be on the bottom? 499. Because it's always 2 times it. No, not 499. 999, yes. You 2 times it minus 1. You have a formula that if you have the top one, it will give you the bottom one. If you have the bottom one, it will give you the top one. I don't care how large a number you want in either of those sets. We know what the other one is. This has to do with not the weirdness of a subset being the same size as the original set. This is a weirdness of infinity. Infinity is a weird thing. If you've ever looked into, almost parallel members and looked at the infinite number of people behind you, or you watched Inception in the movie theater or on your iPhone or whatever, infinity is inherently weird. Yes. Oh, look, you're going to have to really belt it. Shout. Not really. I'm not going to use the term ordinal in the class. And we're using cardinality only for the size of a set. Okay. So if I want to know when 347 is up there, we know 347 is mapped to 2 times 347 minus 1. Yes? Say that again?
What if the subset of n is still infinity?
It's still, there are many infinite subsets of infinite sets. For example, positive integers is a fine set. Positive integers divisible by 3 is a subset of that set that is in fact itself infinite. Positive integers divisible by 793 is an infinite set. It gets fast, big, really, really fast. All the members of it get big, really, really fast. But there's as many of them in there as you want to have. Now I'm going to have a huge bruise on my ass. Very pointy, very pointy. Ow. Sorry. Not important, I know, except to me, because it still hurts. Okay. So let's talk about subsets. S is a subset of T. If, first of all, this is really important, S cannot be a subset of T unless S is a set. Sometimes you guys look at it and say, hey, is Zebstrika a subset of the set of Pokemon? No, it's not. It's an element of. And it's really important that you guys get the difference between subset and element of.
Can you say the set that includes Zebstrika?
The set that includes Zebstrika is a subset of the set of the Pokemon that I had on that first set page. And also the set of all Pokemon that have ever been named by Nintendo, right? Unless you guys are lying to me, because I could believe that you guys made up those names and are just laughing at me. But I would even approve. But, okay, so in this case, S here is a subset of T. Now, it is also possible to say that S is a subset of S, but only if you have the line underneath it. It's sort of like it's completely legitimate to say that 3 is less than or equal to 3, right? But it's not legitimate to say 3 is less than 3, right? Can't say that. So S can be a subset of S, but S cannot be a proper subset of S. Proper subset means that you have to have it, to have a proper subset, there has to be at least one element of the superset that is not in the subset. Okay? Does that make sense? No. Just say it again? Okay, let's do it with pictures. I'll say it, but I'm going to do it with pictures. Okay, how about if I have A, B, and C, and I have another set that is C, A, and B. Okay, we're going to name this set S1 and this set S2. We can say a lot of things, like S1 is equal to S2. We can also say that S1 is a subset of S2, and we can even say that S2 is a subset of S1. What we can't say, bad, stop, we cannot say that S1 is a subset of S2. Because to have a proper subset, the cardinality of the smaller guy has to actually be smaller than the, actually I shouldn't say that because of infinite sets. You have to be able to find one element of the superset that is not in the subset. There has to be at least one unique element, and there could be more than one. I should really not go out there. Yeah, that's good. Anyway, this table is out to get me. I'm going to be black and blue. Okay, so the natural numbers are a subset of the real numbers. Okay, how about the integers are a subset of the natural numbers? No. How do you prove that's not true? Give a counterexample. What's a member of the integers that is not in the natural numbers? -1. Classic, perfect example. But -79, -5,302,000 works just as well. Okay? How about -3 is a subset of the real numbers? No. But the set containing -3 is a subset of the real numbers. Okay, that's important. How about this one? Yep. How about if I get rid of it and I ask for it to be a proper subset? No. No dice. Okay. The set containing X is a subset of the set containing X. True. How about the set containing X is a proper subset of the set containing X? No. Okay, the set containing X is the set containing X is an element of the set containing X and the set containing X. Yes. Yes. The set containing X is a subset of the set containing X and the set containing X. Yes. Okay, last one. Set containing X is an element of the set containing X. No. Good job. I can make it true if I just throw in some more curly braces. Curly braces fix shit. Stuff. Okay, ordered pairs. It turns out when I first tell people about ordered pairs, they think it sounds needlessly complicated and they don't want to know. Guess what? We're going to use them a ton. So you might as well get comfortable with them. I will tell you, honestly, you're more likely to be comfortable with ordered pairs once we start using them. But you guys use ordered pairs all the time in terms of coordinates on the xy plane, right? So all you do is you have two elements and they're in an order. So if you take the cross product of positive integers and positive integers, then you just have ordered pairs that are in the upper right quadrant of your, plane, right? So you can have 3, 3, and 2, 3, and 1, 3, and 1, 2, and all that kind of stuff. Those are just ordered pairs. Ordered pairs turned out to be very useful for a lot of things. When you talk about the Cartesian product of two sets, what you're doing is you're talking about the set of all possible ordered pairs you could come up with. So 1, 3 is a member of the Cartesian product of positive integers crossed with positive integers. Okay. So if you cross two sets, A and B, then any little pair, A is a member of the first thing you crossed, and B is a member of the second thing you crossed. I probably won't talk about it too much, but it's also very common to expand the idea of ordered pairs to ordered triples, quadruples, quintuples, and we call them all together, we call them ordered tuples. And that's where you put a whole lot of things together. If you ever think you want to study databases, then tuples become incredibly important for things like relational databases and things like that. Cartesian product. Let's keep going. I've got more interesting things to say about life. Oh, power set. This is a good thing. Is this on the homework?
Yeah. Yes.
Okay, so I can ask you questions about power sets. I love asking questions about power sets because I can ask you about cardinality and power sets. Very common for me to give you a set and I say, hey, give me the cardinality of this set, give me the power set, give me the cardinality of the power set. Okay? So it's the set of all possible subsets. Now we talked before briefly about how you can represent sets with bit strings. It's very common. Suppose your universe of discourse is equal to the set containing 1, 2, and 3. That's your whole universe. You only have 1, 2, or 3, or A, B, and C. I don't care. Just 3 things. Well, when I talk about the possible subsets of this universe of discourse, or even just your base set, then I can say, well, let's look and see, what if none of the elements are included? What if only 3 is included? What if only 2 is included? What if 2 and 3 is included? What if only 1 is included? What if 1 and 3 is included? What if 1 and 2 is included? And what if all 3 of them are included? You have now counted through all possible subsets of 3 items. You did that by counting in binary. And what that means is that instead of having this be a universe of discourse, sorry, I forgot I need to use the back of my pencil now. Let's call this S. So if the size of S is 3, then the size of the power set of S will be 2 to the third. And I'm showing you why that's true by showing you how I could do, basically I could use the bit string representation of set membership to sort of step through very formally all the possible subsets of set S. Does that make sense? So let's go back to what I prepared about power set. Power sets turn out to be useful for a whole lot of stuff, it turns out. Set of all possible subsets. So if we have, I just used this. The cardinality of the power set of S is equal to S. I don't like the way that's written. If the cardinality of S is equal to, let's say N, then the cardinality of the power set of S is equal to 2 to the N. And the reason why is that whole little thing that I just went through. We spend a lot of time talking about set theoretic operations. I have a collections of little animals, and I, for some reason, picked ones I mostly don't know the names to. But if I have set A and set B, and I take the union, that means I take all of them that is in either set. And it doesn't matter if I'm lazy and I want to just list them all, I could list 6 things there if I wanted to, and it wouldn't change the answer. It's not wrong if I list something pup, right? Lilliput. If I list Lillipup twice in the answer, that's not wrong. There are Lillipups in each set. But it's also not, any better than just listing each unique element. There's only 4 unique elements between the 6 set memberships you can see up there. Make sense? Okay, so the union, big U, union of 2 sets is every object that appears in either set. And there's a set theoretic way to write it that is in your book, and you should probably look at it, but I'm not going to put it on the quiz this week. Now, intersection is listed with an upside down doodle. So union is a U holding things, and intersection is a little mountain. And those are all the guys that are in both sets. Okay? Difference means all the guys that are in only one set. It's like XOR. You have to say set it for A, set difference B, you have to take the guys in A that don't appear in B. That's what you get. Complement is where you get the guys that are in only one set, so you would get this guy and that guy. Symmetric difference is that. And complement is everything in the universe of discourse that's not in the set. Now, it is very common for people to enjoy thinking about these set theoretic operations using Venn diagrams. I just want to tell you right now, Venn diagrams are exceedingly limited. You cannot have an intelligent Venn diagram of 4 sets, for example. You're pretty much limited to 3 sets if you want to use Venn diagrams. On the other hand, while we're getting used to things, it can be very useful. For example, this region in here, that is A intersect B. And this region in here, that is A union B. And this region in here, that is to say everywhere outside the circles, that is equal to universe minus A union B. So that's everything in the universe except what's inside A union B. Yes?
Can we go back and look at the operators?
Sure. We could look at them, you know, like forever and lots. Is this good? Are we good?
Yeah, because I didn't.
Read the sections of the book about this. It turns out, I know a lot of this looks like a lot of PKU and bookkeeping. There's a lot of notation and stuff. You get used to it and it's not so bad. And like I said, for classic set theory, which was what we're doing, we're not talking about axiomatic set theory. We're not talking about the exciting parts of set theory that you have to get at because of Russell's paradox, which I'm going to explain to you what it is, probably on Monday. We're working with the most simplistic definition of sets in this class. If you care about set theory, or you're going to be a mathematician, you're going to learn about things that are way more arcane and exciting about sets than you're going to learn about in this class. Yes?
Can you explain difference complements?
Yeah, sure. Why don't we do it with the Venn diagram? Union. You have 2 circles. You take everything in both circles. Intersection. You have 2 circles. You take everything in the little wedgie. Difference. Difference is we have our universe of discourse. We have A and we have B. If you take A minus B, what you get is everything in A except those things that are also in B. That's set difference. Okay? You're only subtracting you only subtract from A things that are in A. So you don't care about the elements of B that are not in A. You just subtract the wedgie. So another way to say this would be look, I've got my highlighter on. Excuse me. Wait, I'm going to go back to the other slide. Are we okay with the difference? Complement just means if you have a circle, go outside it. It means you have a big pan of dough and you take a cookie form and you take the cookie. Now, so the set is the cookie dough and the complement of the set is the plate of dough from which you have taken the cookie. Okay, it's everything outside the circle. Symmetric difference is just like XOR. If you have 2 sets and there are some things like, for example, the way you do Venn diagrams of symmetric difference is you take only the guys that aren't in the intersection. So then you would do A XOR B would be all the guys in here and all the guys in here, but you don't take any of the guys in the wedge. You're only taking guys that are in only one set at a time. I don't think set symmetric difference comes up as much as the others, by the way. So here's union. And this is important. I have, for each one of these operations, I have a Venn diagram and demonstration of it, and I have the math ease for it. It turns out you can prove all sorts of stuff if you just look down the definition. A union B is the set of all x such that x is an element of A or x is an element of B. This is the baseline for why, if you just understand the way disjunction, that is to say or, works, you can generalize that set of intuitions so that you understand set union. Okay? So now if we go to the next picture I have, A intersect B is a set of all x such that x is an element of A and x is an element of B. This is sort of the bottom line of why all your intuition about conjunction, that is to say and, applies to intersection for sets. Okay, so now if A and B have no common elements, that is to say that A intersect B is equal to the empty set, then we say they're disjoint. They don't have a wedgie. Yes? No, empty set is almost never an element. Most of the sets we're looking at don't have sets as an element. It's a subset of it, but it's not an element. Really important distinction.
So if anything, like, then why you told me like that, like the end of the set with empty set in it is equal 1. If that's not an element, why you say it's equal 1?
When you build a set, it's often built out of very uniform things. For example, it's very common for me to say something like the set of all x such that x is an element of the English alphabet. Every element in that set is a letter, a thing you could be part of someone's name if they're typing it into a website in English. But set theory makes sense if you make completely heterogeneous sets. I could have a set that had the concept of hunger, the number pi, my first boyfriend from high school, all of the planets of the sun Antares, and Kyle's left foot. That is a perfectly decent set. It is not the kind of set we normally write computer programs or databases about. We usually have some sort of the kinds of things that could fit in that field kind of restriction. It is possible to have sets that take other sets as elements. For example, the set of all the subsets. A power set of a set is a set of all the subsets. All the elements of a power set are sets. You would never have a power set that had as an element this set, this set, this set, and 7, right? 7 would never be in there because it's not a set. It violates our type checking is the way I think of it. Some sets could have an empty set as an element of them. Most don't. All sets have the empty set as a subset of them. All have the empty set as a subset of them.
When you show us the table, like A, B, C, and then like 1 and 0.
Those are subsets.
Yeah, I know, but the first one, 0, 0, 0 means you're not taking any of that. That is an empty set.
That's a subset, yes, but not an element.
Sets aren't elements. Well, that's not true.
Sets can be elements. They are not necessarily elements. One of the things that's actually pretty cool about math is how easy it is to lie.
Yes.
When you don't want to, you try to write down something reasonable, and unless you're careful, you aren't writing it down right. Which is why I recommend strongly making sure that you look at all these things. For example, set difference. A set difference B is the set of all x such that x is an element of A and x is not an element of B. These kinds of things allow you to prove a bunch of stuff. Like a bunch of stuff. That's the math-ese for the set theoretic operator. I want to get to the end of this so that I can do something else next time. Set complement, you have your set and you take all the thing outside of it, it's set complemented. The Venn diagram pages in my slides go out of their way to give you the math-ese. We don't normally use Venn diagrams for very much because you can't demonstrate something if you have very many sets. Set operators are incredibly similar to logical operators. So the negation of a logical proposition, B, looks very much the same as the set complement of B. A intersect B, all that intuition works for A union B. A or B, A union B. A and B, A intersect B. And in fact, here's the list of set identities. Okay, guys, see that list? Does it look similar to this? It's exactly the same. And there is a way, I don't think I'm going to go through it in this class, but there's a way to transform any set theoretic identity proof into a proof in propositional logic and vice versa. It all has to do with defining a function that is true if an element is part of the set and false otherwise. Because that sounds a lot like a proposition. Am I making sense? Yeah. Wait, I want to talk to him right now. You with the hat. You want to ask me a question?
Oh, me?
Yes.
Oh, sorry. So U is representative of the universal discourse set?
That can be a little bit confusing. The bold U. The bold U. I'm hoping that you can see the difference between union, let me get a color, between union and universe of discourse. Can you see that?
So is universe of discourse like true and then null set like false?
No. I see where you're trying to go, and you could come up with a situation in which I could answer yes, but not in most cases. The universe of discourse, we're going to be using universe of discourses so much. And we already talked a bit about the bit string representation of sets. We've actually, I'm ahead of you guys for the homework that you're doing this weekend. Usually, actually not completely, because please quick rush to do all the homework that has to do with quantifiers before I lecture on it. I promise you, the lecture will be much better about quantifiers if you've actually tried to do the homework before I lecture it on you. Yeah. Remember, there's a quiz on Monday. Bye. Hi.
Hey, I don't understand the infinite.